Okay, it's 7:30, so let's go ahead and get started. Good morning, welcome to everybody that's joined. My name is Dana Lehman. I'm the Sustainability Coordinator for the Town of Crested Butte, and thank you for joining the Gunnison Valley Energy Code and Building Efficiency for Builders webinar series. Just wanted to start off with a little bit of background, letting you know why we're doing this webinar series and who's bringing it to you. I'm part of the Gunnison Valley Building Code Collaborative, which is really just a group of local municipalities in the Gunnison Valley. So Gunnison County, City of Gunnison, Mount Crested Butte, and Crested Butte. And we received a grant from the Colorado Energy Office, the CEO Code Adoption and Enforcement Grant Program that allowed us to fund not only these webinars, but also a scholarship program, which I'll talk to you about in just a minute. Next slide, Robby. So we had a series of 3 spring webinars set up for y'all. Today is Energy Code 101, Requirements Applied, which is a part 2 to our webinar we delivered last week, which was Energy Code 101, Compliance Pathways. If you missed that, we did send that out to all the registrants, and we also posted that to the Town of Crested Butte Sustainability webpage, which is where all the webinars will be hosted, and they are all recorded. Next slide, Robby. So quickly, I just want to remind folks that as part of that grant, again, we developed a scholarship program, which is the Energy Efficiency Professional Scholarship Program. These QR codes do work, so if you feel like you want to scan them and check that out, please feel free. This funding provides up to $2,500 for any energy, contractor or building professional that serves the Gunnison Valley. So please apply. We want to get that money out to folks, and it's fairly flexible. So if you have any questions about what you can apply for, we are funding certifications, trainings, even equipment for any sort of energy efficiency services. So certainly reach out if you have any questions about what you can receive funding for. Next slide, Robby, thank you. So really quick, just want to address the Zoom hygiene items. So if you have questions during the webinar, please use the Q&A function, which is at the bottom of your screen. If we don't have time to get to your questions, please feel free to email Robby, who is our presenter today. He will provide his contact information. You can also email me, and my contact information is available to you as well. I think that's it. Next screen. Thanks, Robby. And then I do want to acknowledge that we are offering Spanish interpretation today. So if you do need the Spanish interpretation feature, our wonderful interpreters are online right now. You will look to the bottom of your screen. You should see an icon that says English or EN. You click on that and you will transfer to the Spanish channel. Next screen, Robby. Okay, and with that, I will let Robby Schwarz, who is the founder of BuildTANK Inc., take it away from here. Thanks, Robby.
Great. Well, thank you so much. I appreciate it. And thank you all for joining us today on this second part of this series of webinars. I'm Robby Schwarz with BuildTANK Inc. And BuildTANK Inc., we strive to use what we learned in the field to achieve a substantial change in the building industry. And one of the ways that we think that we can help move the building industry forward is to understand codes in a much different way. So one of the things I wanted to start with, because I don't have a lot of preamble, we're just going to dive right into these requirements, is to put the notion that codes are not minimum in the sense that the word minimum doesn't have a negative connotation. We need to remember that when we're building to a code or a program like Energy Star or whatnot, they're setting a threshold that we can't go below, but that doesn't mean that it's a bad threshold. And if you build to the 2021 IECC, you're going to have a high performance house. There's tons of building science in it. and wrapped into the codes for your specific climate there. And the codes are requiring things that we apply in our houses in order to create a home that performs and performs well out there. So our plan today is we're going to talk about some of the requirements in Chapter 1, some of the requirements in Chapter 3. Then we'll get into the specific installation requirements and talk about some of those. And then the air barrier, air sealing, and installation table itself. Now, when we get into the last two items there's a lot there, and we just don't have time to go into each item there. So I'm going to give you the highlights of those items as we go here. So the first thing that we want to look at are the idea of the construction documents and the importance of the instruction documents. We have a lot of requirements that say what needs to be on those construction documents that are detailed out here. One of the bigger things that need to be on the construction documents that is often missing are the air sealing details. And here are some examples of air sealing details. And we'll get into these in a little bit more depth here, but in that air barrier, air sealing, and installation table, it calls out some areas where we need to add supplemental air barriers so that we enclose insulation and that we have a clear understanding of the components of the building that we want inside our building envelope versus those that we want outside our building envelope. So if you look at the drop ceiling, for example, we see clearly that the responsibility for the air barrier system is at the framing level. And the framer needs to understand that they need to get an air barrier up to the bottom chord of the truss. They need to get an air barrier up to the exterior wall there, and then do the overframing for that particular detail there, which brings that entire drop ceiling into the conditioned space. And we'll talk about kind of that idea of sequencing as well, but just wanted to put into your brain there a little bit that the primary responsibility of these air barrier details and requirements are the responsibility of the framer, not the insulator there. The insulator would come in and maybe touch up those details later on. Then the code requires some level of inspection, and it goes from footings and foundations and framing and rough-in and plumbing and mechanical and final inspections, and even re-inspections are required there, meaning that we don't always do things perfectly. We might have to touch up some things and come back and re-inspect them to make sure that they meet the intent of the code. And when you look at the inspection requirements there, you see that the inspections in the code are specific to the energy code itself. So it says that we have to verify the R value and their correct location, but not only their correct location, but their proper installation, proper air leakage controls that are required as well there. And on the mechanical side as well, we can see that we're required to look at the controls and the system installation and corresponding R values, the system air leakage controls, whole house controlled mechanical ventilation requirements. All these types of things need to be inspected, and therefore they need to be installed, and therefore we need to go to the code to understand how we are to install these things so that we have a house that actually works and performs well, which means that the focus of our codes and the focus of our inspections are really looking at how houses perform there. So we can't go into a house anymore and just say, yep, I see pink insulation in the wall, and walk on to my next inspection. There, we really need to ask a couple questions when we look at a particular item in a house. So for example, in this house, I'm looking at the fan and I say, yep, I need a fan in the bathroom to exhaust warm, moist air out of the house at the time it's being produced. So is it there? That's the first question. And the second question I need to ask myself is, has it been installed so it actually works? You know, obviously here I've got ductwork tied in a knot. It's not going to perform there. So I need to know, is it there and does it work? And I need to ask those two questions whenever I'm looking at something that's been installed, because often we install stuff, but we install it so poorly that it's not going to perform. And that's really the objective of the code, is to ensure that we've got things that are going to perform and perform well. Yeah, the insulation's in this house, but I can't just walk on to my next inspection. I need to look at how it's been installed. Has it been installed that like our cavities are trash cans, or has it been installed so that the insulation actually can resist the flow of energy from inside the house to outside the house? Have the air barrier systems been installed in the right spots? Have they been installed continuously so they work? So again, the question is it there and does it work? And then we can ask the same questions with regards to HVAC installation, whether you're installing a duct system or a hydronic piped system. It doesn't matter. We still need to ask the same questions and ensure that the installation is installed and installed well there. Okay, so we're going to move on to chapter 3 here. So chapter 1, we want to make sure we look at. Chapter 2 is all about definitions that are in the code, and we went over some of those definitions last week with regards to how the building thermal envelope is defined and whatnot. And now we're moving into chapter 3. And the interesting thing about chapter 3 that's a little bit new in 2021 IECC is with regards to the building thermal envelope insulation requirements here. So we have to understand that there's some insulation materials that have an R value mark on them, and there's some insulation materials that don't have an insulation R value mark on them. And in particular, those materials that don't have an insulation R value mark on them, we need to have the insulator help us understand the R value of the material that's been installed. So this section of the code is new to the 2021 IECC that basically says that an insulation certificate complying with this section of the code shall be left immediately after the installation by the installer, which is basically saying that the installer has to certify the R value of the material. Because when I go into a house and I look at some of these installation of insulation in these homes, I have no idea what the R value is there. When they blow a wall with blown fiberglass or blown foam, I can make an assumption of what the R value is, but it's all based off of the density of the material being blown in or the number of inches of material that's been blown in. And so we have to have the insulator certify the R value of the installation in correspondence to what they propose to install in that home. And we have to look at the correlation between those two facts there, that we propose to do something in this home to get our building permit, and have we actually executed it out in the field there. So these are types of materials. These happen to all be fiberglass materials that aren't labeled with an R value mark, but we know that a lot of foam products are out there that don't have R value marks on them, and other insulation materials like rock wools or timber boards or other things like that that we need to look at. Okay, now we're going to move into chapter 4. And chapter 4 is where the bulk of the requirements for how we install things in the code are housed there. There is this section of the code, and as I said last week, the word mandatory has been removed from the code, and the word prescriptive has been removed from the code in terms of requirements. So they're no longer mandatory requirements and prescriptive requirements, they're just requirements. And in essence, those requirements are mandatory, they are required for each of the houses there. But we have to understand that sometimes requirements intermesh things that deal with R values and how we install things as well there. So we have to pull those two concepts apart, because anything that has a requirement that's associated with an R value, we learned last week in the compliance pathways, you potentially can trade that off. But it doesn't negate the fact that you have to install that R value according to the requirements of the code here. So this section of the code, this specific insulation requirements, there are 13 items in this section, and we're only going to talk about a few of those items, kind of the high ticket items here. But I'm going to give you this first example that's going to show how we're going to have to pull out the R value requirement that potentially could be traded off. So we don't necessarily have to abide by the R values that are thrown out in this requirement. But then there's an installation requirement as well. And that is with regards to ceilings with attic spaces. So ceilings with attic spaces, you can think of them as ventilated attic spaces here. And so the requirement is telling us that normally we have to, in our climate zone here, we have to install an R60 attic insulation. In other locations, you have to install an R49. So this is saying that you can install an R38 or 49. It shall be deemed to satisfy the requirement for 49 or 60 that's detailed out in the R value table there, which is one of the compliance pathways, wherever the full height of uncompressed R38 or 49 extends over the top plate at the exterior walls and eave there. So the first requirement is an R value thing. That is basically saying if you're following the R value table compliance pathway, you can drop the R value from 60 to 49. And then the second part is the actual installation requirement. So remember, if I choose a performance compliance option, I could trade off even lower than R49. I could maybe put R30. I could potentially even trade off to R0 over the top plate. But if I could make that trade-off work there, unfortunately, or fortunately, I guess, you're probably not going to be able to make such an aggressive trade-off work with the softwares there. But we know that the R value part kind of changes there, and we need to focus in on the installation part. The installation part here is basically saying that insulation needs to cover the top plate for the continuity of our building thermal envelope. Remember, we defined the building thermal envelope as that boundary that incorporates assemblies like our thermal control layer and our air control layer there, and it needs to be continuous all the way around the building thermal envelope there. So we need to have some R value and air barrier materials over that top plate to get that continuity that's there, which means that we have to have also assemblies that can receive the R value that's going to be installed there. So think about how deep the insulation is when you're trying to achieve R38 or R49 insulation over the top plate. It's potentially well over 10 to 12 inches there. And if this is a ventilated attic, you also need room for a vented eave baffle to be installed as well. So this requirement is not only saying that insulation needs to be installed over the top plate, it's also saying that you have to really install a raised heel truss or a raised heel at the eave so that you can receive the depth of material that's going over that top plate there. So it's not specifically called out there, but it is something that we should be looking for there. Now, why do we want the attic eave baffle? Why do we want to install insulation at a specific depth there? Well, when we have insulation and it's installed properly over the top plate there, and we ventilate that attic space, we have the ability of actually wind pushing insulation off of the top plate. So we add an attic eave baffle that directs that air up and over the insulation there, and that air, that ventilation air is designed to move by means that we call stack effects. So as air warms, it rises, and it's supposed to go in through the soffit vent and then out through a ridge vent or other type of high vent space up top on the roof there. And if any of that attic ventilation air is going to go into that insulation, we want it to drop in from the top, because the attic insulation and, it turns out, our rim joist insulation are the two areas where we're not required to have that second side of redundancy with regards to air barriers there. Everywhere else, all other the cavity insulation, we think of the air barrier system as a combination of our interior and exterior air barriers. In this location, we just have one air barrier. So we're compensating for our inability to put an air barrier on the top side of the insulation with, I'm sorry, by allowing or forcing the air to move into the insulation only from the top side of the insulation there. So we want to make sure that the insulation is over the top plate. We want to make sure that the attic eave baffles are installed, and we want to ensure that the ventilation air moves through the insulation only at the top edges of the insulation. And then lastly, we need to ensure that we have a raised heel truss or a raised heel on that end to receive the insulation, the quantity of insulation that we've proposed to put in that assembly there. So there's some design aspects here that we have to take into account as well. Okay, so the next requirement we're going to talk about are attics without or ceilings without attic spaces. So this is basically our raftered ceilings there. And this section allows us to, again, drop that R value requirement from the R value table from R60 to R30, but only for a portion of the attic or a portion of the ceiling that's separating conditioned space from unconditioned space. We're only allowed to do that for 500 square feet of area there. But we have to make some decisions here, because we know, and when we talk from installing this type of insulation, that air isn't smart, and it doesn't know to follow the black arrow here and ventilate that roof assembly there. So if we make the choice to install a ventilated raftered ceiling here, we have to separate the vent space from the insulation so that we can make that insulation work, and we need to seal it up and seal it up well there. So we know that we have to have diagrams of details on our construction documents here. And we know that we have to have these attic eave baffles there. So the detail is going to show that there. And then we need to air seal those in place so that we have separation between the ventilation space and the non-ventilated and the unventilated insulated space, so that insulation is going to work and work properly in that assembly there. Now, you also have the option of building a cathedralized or unventilated assembly as well. And if you do build an unventilated assembly, it actually is going to kick you over to the IRC from the IECC, and it's going to give you all the details that you need in order to build an unventilated attic assembly there. We don't, again, have time to go into all those details, but you need to look at this section R 806.5 in order to understand what you're allowed to do and what you're not allowed to do, the different combinations of spray foam and fibrous insulations, or foam boards, or continuous insulation versus fibrous insulation to make that assembly work and work well. And all the building science has been wrapped into the code to ensure that we're not getting condensation and whatnot. So it's all really about execution, how you're going to execute it and design that assembly to work and work well. Now, another requirement in this section is with regards to the attic eave baffles themselves here. And, you know, it's been in the code for quite some time that you have to install the attic eave baffles if you have a ventilated attic space. They need to maintain the opening size, and they shall extend over the top of the attic insulation. They shall be installed to the outer edge of the top plate so that we can get insulation over that top plate. But this section is relatively new to the code in the 2021 IECC, where it says that the baffles shall be installed continuously. So we often install spot or skip ventilation in those assemblies there at the soffits there. So regardless if we install a vent in every other bay in the attic assembly there, we have to install baffles continuously so that the ventilation air doesn't bypass the baffle and intrude or go into the insulation there. So you can see there are different ways of installing it, but we want that continuity. Now, there are two issues with the insulation at the top here. And that's why I put this kind of stop, don't do that here. One is that we, on the picture on the left here, we have the baffle, but we have a fiberglass bat stuffed in at the bottom that is supposed to direct the air up into the baffle location. And then remember that fiberglass doesn't stop the movement of air. It's air permeable. Therefore, we need to ensure that we're going to put something rigid there, something that's actually an air barrier that can direct the ventilation air up and over the insulation. And the picture on the right here is showing the compression of the insulation. Yes, we've got insulation over the top plate that we talked about, but do we have enough depth over the top plate in order to get the R value that we proposed to put in that assembly there? So these are things that we need to stop for a second and think about when we're designing these assemblies and how we're going to execute them and make them work and work well here. Sorry, I think I had that slide in twice there. Okay, so attic hatches and attic and doors. With regards to attic hatches and attic doors, we need to have access into these spaces, but we don't need, and we shouldn't be storing stuff in those spaces, which means that we're not going to access them continuously or very often. And therefore, they need to be insulated to the same R value as the assembly that they're penetrating through. They need to be weather stripped and made airtight there. And then if we're also installing insulation in a different way in that attic, let's say we put an attic platform in there for storage or for an HVAC system in that attic, we have to create a space that can receive the proper amount of insulation. Otherwise, we're going to have to move from the R value compliance pathway to energy modeling compliance pathway in order to demonstrate compliance with the code. And that's the picture with the thumbs up there. That's insulation underneath an attic platform there. That's an R38 bat. And if I'm using the R value table compliance pathway, I would have to have some means of getting an R60 under there instead of that R38. So all these things are requirements and deal with the installation of these specific assemblies in our homes. Another one is floors. Floors assemblies are difficult assemblies because often those floor assemblies are hanging out over unconditioned space, which means that they need to be insulated. In the past, the code has pretty much had one way of addressing it, which basically said is the first one here is that the insulation needs to maintain permanent contact with the subfloor. Well, we realized that we want to use those floor systems to maybe put duct in it or hydronic piping to heat the assemblies or other things. So we might want to move the insulation from the subfloor down. And so this code spells that out in a much more realistic and understandable way here. And it says that you can drop the insulation from being in permanent contact with the subfloor if you pay even more attention to the rim board of that assembly and ensure that where these blue dots are, that we're getting air sealing at these blue dots all the way around that rim joist of that floor assembly there. To make sure that we have an airtight assembly and that air isn't moving in and out of that assembly, reducing the effectiveness of the insulated assembly there. So if you are building floors over garages or cantilevers, this section of the code is something that you really want to look at to ensure that you're going to get an assembly that works and performs well. Basements are another part that's called out specifically here in this section. One of the nice things about this section of the code is it really defines well what an unconditioned basement is versus a conditioned basement. And that's different from a finished basement and an unfinished basement. You can have an unfinished basement in a conditioned space, but an unconditioned basement is a basement where you're redefining the thermal boundary of the house to separate the basement from the house. And there are all these requirements that have to be installed if you're going to do that, including an airtight insulated door between the conditioned space of the house and the unconditioned space of the basement. So you want to look at those. And then we get into how do we address actually conditioned basements? Well, we need to insulate it from the top of the basement wall down 10 feet below grade, or the basement floor slab, whichever is less there. So basically the continuity of the insulation all the way down that basement wall from the top at the sill plate to the slab at the bottom there, which brings us to slab floors as well. So slab floor insulation is something that is crucial to ensure that we have a high performing house when we have slab on grade construction. But we also have to remember that walkout basements are basically slab on grade construction as well. So that walkout needs to be addressed. And then as we start stepping up the foundation to enclose the rest of the basement, we need to wrap that crawl space or slab foundation around the sides of the house, at least 10 to 20 feet into that walk-up foundation wall that is creating the context of our rest of our basement there. But anyway, we need to ensure that we install the insulation and now in the 2021 IECC, we have to install the insulation down and or out or have it continuous at the slab edge for 4 feet instead of 2 feet. That was the requirement in the past there. So some of these pictures are interesting to look at. If you look at the upper left-hand picture there, you see that the insulation is replacing the expansion joint. Now, the density of these insulations are such that when you walk on it or you put tile on it or other floor coverings on it, you're never going to notice that there's 2 inches of insulation there. But if you're pouring a stem wall and then the slab up to the stem wall, it's a great technique to install your insulation there as a replacement for the expansion joint, because you don't have to deal with all the details of installing the insulation on the exterior of the house. So the middle picture on the right side here is showing some of that details. You have flashing details or stuccoing details or combination of both in order to protect that insulation during the construction process and also after construction, because a certain portion of that insulation sticks out above grade there. So that's a very difficult detail. So if we're not pouring a monolithic slab, we want to ensure, well, it's often easier to install that insulation as a replacement for the expansion joint. Now, the picture on the left-hand, lower left-hand corner here is a more monolithic slab, but you do have the insulation as a break between the 2 slabs. So we often install in a monolithic situation, we'll install the porch slab and the house slab together, all at one pour of concrete there. But we're not easily able to get a thermal break between those 2 slabs, because one is outside the building thermal envelope as one is inside the building thermal envelope. So we want to make sure that you always get a thermal break between different types of slabs that are inside the house versus slabs that are outside the house. So we think often about the disconnecting the porch slab from the house slab or the garage slab from the house slab, for example, there. And then the last picture I wanted to point out was the picture in the lower right-hand corner and the upper right-hand corner. It says that we have to extend down 4 feet, but it doesn't mean we have to go down 4 feet vertically. We can also include horizontal insulation there, as long as we have a total of 4 feet of insulation that's protecting the slab edge. And remember, in the R value table, that is the R value table, and R value for slabs is calling out the slab edge R value, not the insulation that needs to go underneath the slab if you have a heated slab. That's a whole nother R value that's called out specifically in the footnote for that table there. But in your climate zone, you're going to want at least an R10 exterior slab edge insulation. And if you're heating that slab as well, you'll want an R10 below that as well. Okay, we have a couple more that we're going to talk about in this section, which is with regards to crawl space walls. So we shouldn't be building ventilated crawl spaces, especially in your climate zone. You want to treat that crawl space like a little conditioned space that I'll show you here, and basically build a conditioned crawl space. But if you were to build a crawl space that was ventilated, you would define the building thermal envelope up at the floor level there, and you would have to treat it like the floor insulation section that we just addressed there. And so we often don't sheathe the underside of that floor assembly there. Put OSB or foam board or some type of rigid air barrier on the side to the ventilated crawl space there. And that's what is now required there. So that's a pretty different requirement. So I wanted to point that out. But most often we're going to actually be building an insulated, conditioned crawl space. You can think of it as a small little basement there. So we have to have the thermal envelope is redefined so that we're not putting the insulation in the floor system. We're now putting it on the exterior building thermal envelope walls there. We have to have a rock solid air barrier and vapor retarder on the soil to separate the soil from the house and the gases and air that could be migrating up through that soil there. And then we have to condition the crawl space a little bit. And there are a variety of different ways we can condition it. This is showing a forced air system that has supply air flowing into the crawl space. And then we would have maybe some type of transfer grill from the crawl space to the house so that the return system on a forced air system could pull that air out of the crawl space, recondition it, and then send it back through the supply. So we have a constant airflow through that crawl space, and we're thinking about it as a conditioned space, like a small little conditioned crawl basement instead of a ventilated basement there. Okay, so there are some other requirements in that section of the code that we are going to talk about. Things for sunrooms and masonry walls or steel framing and those types of things. So if you happen to do any construction that's associated with that, you'll want to look at that section. But I just wanted to make sure you know that that section of the code is there, and there's some important requirements for how we install things. Now, where we're going to spend the bulk of our time is here in the air barrier, air sealing, and insulation installation section of the code. This table is set up with the components down the left-hand side of the column, the air barrier requirements down the the middle of the column here, and the insulation installation requirements on the right side of this table here. These components that are called out are specific areas where through inspection we've seen issues over time. So, but you should also think of them as an example of it, because you'll see here in the first column here, it says that we have to have a continuous air barrier and that breaks joints in the air barrier needs to be sealed. So basically everything that is called out in this table for a specific component. If you see anything similar to that anywhere else in the house, you also have to address it there. We're just pointing out common areas where you're going to run into issues where you need to think about it. Now, the components that are listed on the left-hand side here that are bullet pointed there are areas that have been updated in the 2021 IECC. And we're going to go through some of those in particular here. But before we do, I wanted to remind us about the building thermal envelope depiction that is a requirement that has to be demonstrated on your construction documents, because we have to clearly be able to define the building thermal envelope, which is that part of the building, the assemblies that create that boundary condition between conditioned space and unconditioned space there. So from the code perspective, we generally think of a primary exterior air barrier. we have our thermal barrier in between, and then we have our primary interior air barrier. And that's how it's demonstrated in this depiction here, but you can depict it in a variety of different ways on your construction documents. The definitions go into a little bit more detail to talk about the assemblies that need to be joined together to create the air barrier part of the building thermal envelope here. It could be a single material or a combination of materials. So that's why sometimes a builder might say that my air barrier is on the exterior of the house, but that doesn't negate the fact that the interior air barrier system helps the performance of the insulation and also the performance of that primary exterior air barrier system in this kind of belts and suspenders approach that the code is really looking at. And then we have to have the continuity of that air barrier system there. So from the perspective of the code, again, we're talking about a primary air barrier on the interior of the house, which would be the continuity of our drywall system all the way around the house, the continuity of our exterior primary air barrier, which generally is our exterior sheathing, and we have to have continuity of both of these things. And that's what this table, the air barrier insulation and air sealing table, is getting at, is where we don't have continuity. It's pointing out that we have to add a supplemental air barrier in a number of locations there. And the code also talks a little bit about the attributes of air barrier systems that we're thinking of installing here, like the continuity of that air barrier system. But air barriers also need to be strong. They need to be durable to be able to last the life of the house. And therefore, we want to think about what type of materials we're using for those air barriers. Rigid materials are often more durable than flexible air barrier systems there, and flexible air barriers are often more difficult to install than rigid air barriers there. So when we're talking about supplemental air barriers, often we recommend rigid air barriers. If you're talking about a whole system like a smart air barrier vapor retarder system there that's flexible material, well, you have more leeway to install it. You have less obstructions that you have to work around when you install it, because you're installing it at a specific sequence in the construction process there, and therefore you can ensure that it's getting installed and installed well and is going to be durable over the life of the house. But with regards to this table, we're really talking about the stiffness of the air barrier. So we like rigid air barrier materials as supplemental air barriers, things like thermoply or OSB or foam boards or those types of things to make them work. Now, we talk about the continuity of the air barrier. That's one of the first things that the table is getting at. And here's an example of continuity and discontinuity here. So the picture on the right was framed correctly. And again, it's sequencing issues and framers' responsibility here. They installed the sheathing, and in this case, the weather-resistant barrier first, and then they installed the porch roof framing second there. On the left-hand side of the picture, they did it in the opposite. They installed the porch roof first, and then they installed the sheathing second there, and we have this huge connection between inside the house and outside the house. We don't have the boundary condition of our building thermal envelope that is separating conditioned space from unconditioned space. So getting in here and actually fixing that is very difficult. And that's why we want the framers to understand their responsibility and why we need these construction details on the construction documents to ensure that the framer understands we need to have the continuous air barrier and exterior wall sheathing installed first, and then they can install the raftered or whatever trussed porch roof assembly second there. So these details are very important to relay the knowledge and understanding of how we're going to build this house from the architect out to the actual people building the house there. Okay, so let's start with the general criteria. I've taken that table, I've broken it apart here to the air barrier criteria and the insulation installation criteria. This is the first component on the table. That's the general air barrier, thermal barrier requirements. We have to have a continuous air barrier. We have to seal all the breaks, joints in that air barrier, and air permeable insulation cannot be used as an air sealing material because air moves through that material. A lot of times we see fiberglass bat stuffed in a hole, and it's not going to stop the movement of air through that hole. Fiberglass will filter the air and it will turn black over time as it's filtering that air through the material there. This picture is going to come back and haunt us later, so remember that picture and we'll show where it's going to show up. So we need to stop installing fiberglass as an air barrier, and we have to help train our contractors to understand that this material doesn't stop the movement of air, and if you add a little bit of foam to it, it's still not going to work as an air barrier system there. So one of the things we're going to learn here is that we need to install the air barrier first, then we need to cut a right size hole through the air barrier, pass whatever we want to pass through that air barrier, and then seal it up properly there. The objective of the insulator is to add that little additional piece of air sealing foam. The objective of the framer is to get the air barrier up in the first place, and then the other subcontractor might cut the right size hole there. So it's everybody's responsibility to ensure that we get these assemblies working and working properly there. The next one is dealing with ceilings, drop ceilings, and attic accesses that we've talked about before. These same type of assembly details here, but it really stresses and shows the importance of sequencing and the responsibility of the framer versus the insulator with regards to getting that primary air barrier up in the first place here. So in this case, I've got this huge drop ceiling. I've come into the attic and I say, oh no, what in the world am I going to do to make this work? Well, it would have worked much better if the framer had understand that they needed to get the air barrier to the exterior wall installed, the air barrier to the bottom cord of the truss installed properly, then do the overframing for that drop ceiling. And then me as an insulator, for example, I could insulate evenly over the top of that, and that whole drop ceiling is brought into the conditioned space of the house here. So again, if we have these proper details on our construction documents, we can take these difficult assemblies to insulate. Yeah, they're aesthetically kind of beautiful. They create texture inside the house. It's visually beautiful to look at, but they're very difficult details to deal with to get assemblies that actually perform and perform well there. So these details need to be called out on the construction documents there. Another component of this on this table are the walls, the exterior insulated walls. And it says that the junction of the foundation and the sill plate need to be sealed. The junction of the top plate and all exterior walls need to be sealed. We need to address knee walls there. And did you know that exterior corners and headers, those type assemblies have to be insulated? Well, has anybody talked to the engineer about that? Because some of these assemblies need specific engineering, specific details. Well, it doesn't negate the fact that they also need to be insulated. So we have to have some coordination with the architect and the engineer and the builder to understand how are we going to insulate all of the headers and exterior corners there. And then it just continues to talk about sound installation practices, like the insulation needs to be in substantial contact and continuous alignment with the air barrier. In essence, insulation needs to be in contact with the surface that it's intended to insulate. So let's talk about some of these requirements. We use sill seal, that big blue roll in the picture on the right here. Sill seal should not be called sill seal. The sealing part doesn't actually happen in most cases there. It should be called sill capillary break because the sill seal is actually required to be installed to be a capillary break to ensure that water that is drying out of our foundation or might be sucked up by the porous concrete from the exterior doesn't migrate into our wood assemblies there. So it's crucial that the sill seal is installed, but we also have to understand that sill seal doesn't create an airtight assembly there. So we have to seal the sill plate to the foundation. And you can see the pictures on the left-hand side here are demonstrating some of the new products that are out that are compatible with concrete and wood and can be used to seal those foundation assemblies there. So we need, if we're going to put sill seal in, and we can rely potentially on air sealing foam as well, the picture in the middle that just popped up here, but the sill seal actually has to be installed underneath the sill plate in order for that to work and work well there. Otherwise, we basically have to seal on both sides of the sill seal to make it work. So again, like I said, there are a variety of new products and techniques out there that are demonstrating how we can make sill seal be an air sealing material, like the picture on the left here, where we're using 2 coats of flexible caulk to work, or we're using liquid flashes like the picture in the middle, tape products like the picture on the right, or what's called an EPDM gasket. That's the gasket that the individual, the builder, is holding in his hand there. All different types of materials that can be used, but the crucial requirement here is that the sill plate is actually sealed to the foundation there, in addition to the capillary break that has to be installed there. Now, the junction of the top plate and the top of exterior walls is also called out here. And this is where that picture comes back to haunt us here. So air is moving out of the house through the top plate connection to the drywall, wherever that top plate is exposed to the exterior. So exterior walls it doesn't just mean the 4 insulated exterior walls if I had a square house. It means any wall that is adjacent to the exterior, to the ventilated attic space, for example. So we have a top plate. I'm standing up in the attic and I'm looking down at the top plate, and you can see the drywall connection to the top plate isn't very tight. There's a gap there. It can be a large gap or a small gap, but if you multiply the lineal feet by the gap dimension there, you're going to get a large hole to the attic space there. So if you've ever taken part in a blower door test and you've seen air leakage from an interior wall outlet, this is where the air is coming from. It's coming down from the attic, or that air is either coming down or moving up through the outlet to the attic space there and going in and out of our buildings. So the code is saying we need to gasket or seal the drywall to the top plate of any wall that is adjacent to the exterior, any wall top plate that is adjacent to a ventilated attic space here. So interior top plates and exterior insulated wall top plates all need to be done. This happens to be a great use for sill seal because the surface is actually straight and flat, and you're using screws to mechanically fasten that drywall and squish it down and create a gasket there. But you can also use flexible caulking materials or other type of gasket materials to do this connection here. And we need to have a conversation with the drywaller because it fundamentally changes the way that the drywaller is going to install the drywall in these houses there. They often will scrape it off or pull it off in the installation unless we have a conversation with them to understand why that material is there. So we need to inform and educate all of our trade partners. The next thing that's talked about is knee walls. And knee walls are exterior insulated wall assemblies. They're wall assemblies that are adjacent to ventilated attic spaces, and that attic space is often accentuating the temperature that's outside, especially in the summertime. The attic temperature is well in the 150 range when it might be just 90 degrees outside. And in the wintertime, it's definitely tracking the outdoor exterior temperature. So we need to insulate these walls, but we need to insulate them so that the insulation actually works, which ultimately means we need to frame these walls so they actually work there. Which means that we need a top plate, a bottom plate, side studs, exterior attic side sheathing, and then our cavity is set that can be insulated, and then we need to be able to actually drywall it and get that 6-sided enclosure on the insulation there. And again, we should have details that are detailing this out in our construction documents to ensure that it's going to work and work properly there. Now, the problem that we're starting to see is that we have complex knee walls that are being defined by attic truss systems and roof truss systems that are creating these assemblies there. Now, the first thing is that they're often 2x4 assemblies versus 2x6 assemblies, which would automatically mean that I can't use the R value table compliance option. I have to go to a software compliance option there because I have to describe how I'm going to insulate a 2x4 wall assembly versus a 2x6 wall assembly. Then I'm going to have to overframe these assemblies here to be able to get a top plate, a bottom plate, the side studs, the exterior or attic side insulation there, and make this assembly work. I have to work with my framer to see that this is an area that needs to be framed differently and that it's their job to actually do it. The picture on the left here brings in another issue, is that sometimes these gable end trusses are on edge, and I only have 1.5 inches space to frame, and I mean to insulate. And so I'm going to have to overframe that so I actually get a cavity that I can insulate. I need at least a 3.5-inch cavity in order to get insulation that's going to work and work well in this high-performing house that we're building to meet the 2021 IECC. So all these details need to be thought about: how we're going to insulate it, how we're going to design it, how we're going to create assembly details that somebody can read and execute in the field, and then ultimately understanding that it's the framer's responsibility and training the framer to see it in the field and then execute it properly. Get the air barrier. In general, it's always about getting the air barrier up first and then doing any overframing that you have to do to bring it into the conditioned space of the house. This section also talks about the insulated headers and insulated corners that need to be installed in these assemblies there, and getting details on the construction documents that show how you're going to successfully do that, like the header details here or the wall details here. So ultimately, what we're trying to do is define where the thermal boundary is. Do we want that fireplace or this double wall assembly to be inside the conditioned space or outside the conditioned space? And then we have to make some choices about how we're going to execute it so that we are following our plan here. So in this case, we're designing these assemblies to ensure that the exterior wall is our thermal boundary and that the duct or chase is brought into the conditioned space. So I can create details where that's going to actually happen here. So I've got a double wall assembly, and I'm bringing that double wall assembly into the conditioned space by putting the supplemental air barrier or the interior air barrier to the outside wall here. If you look at the chase on the upper left-hand corner here, that duct is really outside the conditioned space or outside within the building thermal boundary here, because I've missed the supplemental air barrier here. The detail below is calling out the need for that air barrier installation that would bring that duct into the conditioned space of the house here. So again, make a choice. Do we want the assembly to be inside or outside the building envelope? And then we can figure out how to align the air barrier systems to bring it inside or to exclude it and take it outside the building envelope there. Another component in this table is the rim joist here. And the rim joist shall include an exterior air barrier here. And it basically is talking about the rock solidness of that air barrier system here, because we're not required to have an interior air barrier at this particular assembly. So we're focused on that junction of the rim board and the sill plate and the rim board and the subfloor to ensure that we get an airtight assembly there. And then we need to make sure that the insulation maintains permanent contact with that rim board, because again, we don't have the requirement to install an interior air barrier or supplemental air barrier on top of that insulation there. So I would hasten to bet that if you go out to your job site and you look at the rim joists of your assemblies there, that you will see gaps between the rim board and the sill plate and the rim board and the subfloor. And those gaps are required to be sealed up. There are other gaps like the sill plate to the foundation that we talked about that need to be sealed as well if you have a rim joist to a foundation. But we also have a rim joist between floors, between the first floor and the second floor of a home that need to be dealt with, and to ensure that we have continuity of our air barrier assembly there. So we have leakage happening in these different locations, and we need to be able to ensure that we're able to air seal that assembly well, which means that the sill seal needs to be fully underneath the sill plate in order for us to air seal that assembly. So this requirement is asking us to seal the rim board to the subfloor, the rim board to the sill plate to the foundation. And yeah, wouldn't it be great if we had a detail that demonstrated the need for doing all of that, either at the foundation connection or between floor connection here. And then we need to insulate it correctly. These are pictures of like the pictures in the middle there, where the insulation is not in contact with the building thermal envelope there. So it's that crescent shape is a telltale sign that the insulation is not touching the rim board there. And in the picture in the upper right-hand corner, the IR image there is demonstrating that the insulation is not functioning properly because it's not in contact with the rim board there. So we're seeing a lot of builders move to spray foam specifically in this location because it fully fills the cavity. The insulation is in contact with the rim board. It's actually air sealing as well. And then we just need to ensure that that foam is taken over the the sill plate and is in contact with the foundation to get that extra additional air sealing that's happening there as well. Floor systems are called out specifically here, that we have to maintain the air barrier of that floor system, and then it takes us over to the floor section in that specific insulation requirements, the R402.2.7 floor section, for how we insulate it there. So we have a floor over a garage versus the floor over the conditioned space of the house. We have a common wall that's separating the conditioned space of the house from the unconditioned garage there, or the non-habitable garage space. And we have to address the floor system and do all the air sealing to separate the floor from the wall. So you can think of floor assemblies as wall assemblies that have just been laid flat there. And when they're laid flat there, we have to have 6-sided enclosure of the insulation that's been installed in that assembly there. So we need to make sure that any possibility of air leakage into that assembly is taken care of. And we need to separate the insulated floor assembly from the non-insulated floor assembly that may be adjacent to it there. So that we have to get that blocking between the insulated floor assembly and the non-insulated floor assembly. And then we need to air seal it and air seal it properly there. similar to what was described in the rim joist section of this table here. And then we need to remember that sometimes cantilevers show up in strange places, like on the first floor to the garage there. So we need to address it wherever we have floor hanging out over unconditioned spaces there. Okay, basement, crawl space, and slab foundations here. What we're really getting at here is getting a clear air barrier between the dirt or slab and the conditioned space of the house here. So we've already talked about that with regards to crawl spaces, getting an air barrier and vapor retarder against the dirt floor. But what if we have a slab? We also need to air seal that slab. If we have a sump pit penetrating through that slab, we need to have airtight sump pit covers there. We need to make sure that any plumbing or electrical conduit is sealed to the slab, that any cracks in the slabs are sealed there and made airtight. So that's the big thing with regards to slabs, is that the low side holes and the high side holes are the most detrimental holes in our building thermal envelope because they're always seeing the pressures that are created by stack effect, which is just describes the ability of air to warm and rise and leave on the high side of our house. And whenever it leaves on the high side of our house, it comes back in through holes on the bottom side of our houses here. Shafts and penetrations are another detail that really demonstrates the need for the framer to see the shaft penetration and to get the air barrier up first before it is ever penetrated here. So the picture on the right here, we've added things through that shaft penetration to the unconditioned attic space, and it's very difficult to get the air barrier up first. So what we're looking for here is to always get the air barrier up first, then install and cut a right size hole through the air barrier and pass whatever we're going to pass through the air barrier, and then we're going to seal it up properly. So number one, installing the air barrier is almost always the responsibility of the framer. Cutting the right size hole is generally the responsibility of the trade partner that's going to be passing, the HVAC contractor that's going to be passing a duct through it, or the electrician or the plumber who's going to be passing something through that specific air barrier. So we want to make sure they understand to cut a right-sized hole. And then the insulator's job is just to touch it up with a little bit of additional air sealing foam at the end here. What we're learning more and more is that one hole for one item passing through that hole works a lot better. So this picture on the left here is showing a lot of holes through the air barrier, but it's much easier to air seal it and or flash it than it is trying to put multiple things through that hole. You can see a small example here with the wiring in the lower right-hand picture here, how difficult it is to air seal all of these little holes through that the wiring is creating in that particular assembly there. And as we want to get our houses tighter and tighter, these little holes matter more and more in our assemblies here. Garage separation. So the garage, even if you have a conditioned garage or a heated garage, it is never a habitable space. It always needs to be clearly separated from the house where you're actually living and breathing and sleeping in there. So these are complex assemblies. They have cantilevers out to them. They have sometimes mechanical systems out to them. They're difficult assemblies, but we need to ensure that we use all the principles of this table to clearly separate the garage from the house. Even if it's a heated garage, it is not part of the conditioned square footage of the house, and it should never be part of the volume of air of the house as well, because we store our cars, we store gasoline, we store pesticides. All of those nasty things are getting into the air, and we want to ensure that that air doesn't get into the house as much as possible. Showers and tubs on exterior walls. Again, we need to bring that tub assembly into the conditioned space of the house. So we're going to install an air barrier between the tub and shower seat or shower pan and that exterior insulated wall assembly there. And we should have details on our construction documents that call that out there. In this case, they're going to use a blown fiberglass or cellulose to insulate it here. So they've installed the air barrier first. They've cut holes in the air barrier to put a fill tube for the insulation to get blown into those assemblies. You see the cross blocking here. So the framer might have an additional job to ensure that the holes are cut for the insulator to successfully insulate the assembly, because the insulator might not recognize or know that there's cross blocking here that's been installed, that assembly needs to be insulated in 3 or 4 segments versus 1 segment there. Ensure that those air barriers are installed first before you install the tub or do any framing for kind of the fancy decorative tub surrounds that we have for the seats that go into showers on an exterior wall. All those things, you need to get the air barrier up first and then bring it into the house. Now, over the course of time, fireplaces that are installed on exterior walls were part of the, actually detailed out in the code, but now they aren't. And so we want to ensure that we use the principles that we're learning from the requirements for installing air barriers and supplemental air barriers for fireplace assemblies as well, if they're on that exterior wall. So again, get the insulated wall, address it first, get the air barrier installed first, and then do all the overframing for that fireplace. On the left-hand side here is an example of where it happened in reverse. So they went in afterwards to try to get and piece air barriers back in this assembly, and this was the result. And you can see the pictures on the left-hand side here, how difficult it is to get a continuous air barrier installed afterwards. So again, that sequencing is super crucial, getting the details on our construction documents to ensure that we get the air barrier up first and then do the overframing, which means depending on the insulation that we're installing, we may need to pre-insulate these assemblies as well before we get the air barrier on the interior side up there. So the next one that we're going to talk about are electrical foam box and other assemblies that are put into our exterior building thermal envelope. These electrical boxes can either be airtight boxes that are installed first and are airtight and gasket to the actual drywall there, or like is shown in the picture on the right, can be our typical electrical box that is leaky that we've made airtight by the installation of some air sealing foam on the backside of the box where the wires penetrate. But we also need to seal that box to the drywall that it's penetrating through the building thermal envelope. So these other potential areas that we need to seal to the surface that they're penetrating would be bath fans, plumbing, wiring, HVAC boots that go through the building thermal envelope have to be sealed to the surface that they're penetrating through. Now, the picture on the right here is the bath fan. We often cut out the bath fan opening way bigger than the fan itself. And so we have direct connection between inside and outside. That all needs to be air sealed. And my projection is in the future that we're going to be required to install airtight fan housing, just like we're required to install airtight can lights within the building thermal envelope of our assemblies here. So that, again, that boundary between conditioned space and unconditioned space where air leakage happens. Now, as we get our houses tighter and as we are required to build it tighter and tighter, which we want to do because we want to gain control and predictability of the airflow, the moisture flow, and the thermal flow that's happening through these assemblies, we start seeing things that weren't big issues from air leakage in the past become a big issue for air leakage now. And one of those areas would be traps, plumbing traps here should get air sealed. We're starting to see condensation form on the backside of tubs and whatnot that can be avoided if we reduce the amount of air that potentially can get behind those assemblies here. Whoops, I'm going the wrong direction. Okay, we're going to end up here with regards to single family and attached houses. Here, the attached housing, we're starting to see more and more interest in building attached housing for a variety of different reasons there. But what we know from a performance perspective is that often the attached housing is leaking 2 or 3 times more than the single family house that is twice as big as that attached dwelling unit there. And the reason is primarily because of the assembly that we've chosen primarily to use to build attached housing, which is this shaft liner area separation wall. Now, the green part of this wall assembly is the fire assembly that is trying to keep fire from one dwelling unit to the other dwelling unit. The framed portion here is held off of the fire assembly by a 3/4 inch gap. And that 3/4 inch gap is open directly to the outside at the front of the building, at the top of the building to the ventilated attic or to the roof assembly there, and to the front, the back of the building there. Now, I'm going to go back real quick here. We have often very little leakage from unit to unit, but we have this direct connection to the outside that is creating the leakage in it. And now these are the UL listed assemblies that are described with those numbers at the top of the slide here. We are now allowed to actually air seal these assemblies here. And you can use some air sealing foam, but you still have to have what's called draft stopping, which is a fire stop that is pushed into that gap. Usually it's a rock wool assembly, so you want to push that into the gap first, and then you want to air seal that gap, and in essence you want to picture frame that gap there to ensure that we're getting the assembly sealed correctly here. And if you ever need to know, it's called the BXUV guide, and the BXUV guide details out how we can air seal these assemblies and what type of air sealing foams we can use to air seal those assemblies as well here. The other trick with these common wall assemblies is use all the components that we learned in table R402.4.1.1, the air barrier, air sealing, and insulation installation requirements there against that exterior wall. So if I have a tub against that common wall, I want to get the air barrier installed. If I have a fireplace against that common wall, I want to get it installed, get the air barrier installed. Sometimes you'll have a vaulted ceiling and you'll have basically a knee wall against that common wall. You want to frame it just like you would frame any other exterior wall, knee wall. Use all those principles and you're going to get an airtight assembly, and we're going to be able to separate that particular dwelling unit as an airtight assembly and test it and make it meet the requirements of the code here. I'm going to end on a couple other requirements that we need to know about. For example, lighting requirements. You used to have a percentage of what we call high efficacy lighting has to be installed. Now all the lighting has to be high efficacy lighting, basically LED lighting in our houses. There are also some requirements for interior and also exterior lighting controls. That the lights don't remain on continuously there. So you want to look at those requirements in the code. Lastly, or as we move to an end here, we see that there's some new testing requirements. We not only have to test for house tightness with our blower door and our duct tightness with a duct blaster, but we also now have to test for ventilation testing to ensure that the ventilation flow through bath fans, kitchen hoods, and whole house control mechanical ventilation meet the requirements of the IRC here. There is one exception with regards to kitchen hoods, but this is a new test that we have to do here. Again, we have to test for blower doors testing, or the air tightness of the house here, and that also triggers our need for a whole house controlled mechanical ventilation in our houses here. So air leakage testing is required by the code. We also have to design our HVAC systems, whether it's a hydronic system or a forced air system. We have to do a manual J that calculates the load for the house. We have to do a manual S that ensures that we have equipment that has the right capacity to meet the load. And we have to do our manual D, which is our duct design or our hydronic layout for that particular house here. Testing of these systems is changed a little bit, or the requirement, because there's a realization that in the sections R405 and R406, you potentially could trade off house leakage for more R value in the assembly. It's kind of a perverse trade-off that doesn't happen very often, but the requirement now says that they basically put in a backstop that says you can't trade off to a house that's leakier than 5 air changes per hour. They also put in an exception for attached housing and small dwelling units, where you can use a CFM per square foot of building enclosure area metric instead of an air changes per hour metric, which is penalizes small houses and attached housing. So you want to make sure you understand those metrics when you're dealing with small houses, 1,500 square feet or smaller, and attached housing, and understand that the true metric of 3 air changes per hour in our climate zone is still the true requirement. And that's documented in section R402.4.1.3 there. You have to document your blower door test here with a report, and when your house is airtight in climate zone 7 and 8 now, which climate zones that you'll be dealing with, you are now required to install whole house mechanical ventilation that is balanced ventilation strategy that has a specific heat recovery of at least 65% at 32 degrees there. So make sure you understand that. If you're doing any forced air systems, you'll also be required to do duct leakage testing. And now in the energy code for the 2021 cycle, you have to test ducts regardless of where they're located. In the past, you only had to test ducts if any portion of the duct was outside the building thermal envelope. In the 2021, you have to test regardless of where the ducts are located, but you're given a slightly larger duct leakage requirement. If those ducts are inside the building envelope 100%, you're allowed to leak basically twice as much as you were allowed to leak before. So 8 CFM per 100 square feet of conditioned floor area versus 4 CFM of 100 per 100 square feet of conditioned floor area there. So I rushed through that a little bit because I know we were running out of time, but I wanted to make sure that we honed in on those requirements, that we understand whose responsibility the requirements are. We're building a house as an integrated system. So that idea of synergy, where different things come together to achieve something that we couldn't achieve before, is really coming forward in the construction of our houses for the 2021 IECC. We're understanding that air barrier systems help us gain control and predictability of airflow, thermal flow, and moisture flow in our houses there, and that the air barrier and the thermal barrier and the assemblies that create those things create that boundary condition between conditioned space and unconditioned space there. So we're applying the building science that's wrapped into the code through these requirements that are detailed out in the code. And we need to get those details on the construction documents so that our trade partners and our builders can really understand how to execute a house that's going to meet the requirements of the code, which is a house that is going to be a high performance home in your particular climate zone that you're building in. So happy to stick around and answer any questions or listen to any comments. But if you have ones that we don't get to, don't hesitate to reach out to me directly as well.
Thank you so much, Robby. Really appreciate your time today. I know for me, having listened to the last webinar, it was really great to hear this all applied, what it really means for builders when they start to plan for their homes or get out there and start cranking out construction. So before we jump into any Q&A, I just want to remind folks that this webinar was recorded. It will be posted on the Town of Crested Butte Sustainability webpage, as well as we hope to get it on the Gunnison County webpage. So keep an eye out for that. We will also send the recording to all of the attendees and anybody who registered for the webinar today as well. I've been keeping an eye on the Q&A box, and I don't see that we had any questions during the webinar. So I'd like to invite folks to either put their questions in the Q&A box, or we can use the raise hand feature and I can actually let you come off mute so you can ask your questions. So we'll give just a few minutes for folks to think of questions, add those, or raise their hand. But if we don't have any questions in the next few minutes, we'll go ahead and just end early. And again, please feel free to reach out to Robby if you have unanswered questions from this webinar. Okay, I see. Oh, just a comment, Robby, is super helpful from somebody in the chat. Okay, I'm gonna give maybe one more minute for folks to place a question in the question and answer box, where I don't see any raised hands, so I'll
I'll just give a quick teaser for next week.
Sure. Thanks, Robby.
So next week, we're going to be talking about infiltration and exfiltration and ventilation with regards to the required manual J, D, and S there. So we're going to talk a little bit more about the differences between infiltration and ventilation. And then we're going to go through some of the key things that we need to look at in our manual J calculation so that we're ensuring that we're getting right-sized mechanical systems in our houses.
Thanks, Robby. Okay, I'm going to assume that there are no questions just during this webinar. So I will end early and let folks go. Thank you all again so much for joining. And please feel welcome. We encourage you to reach out with any questions to Robby, or my contact information is on the sustainability webpage for the Town of Crested Butte. So thank you all and have a wonderful day.
Thank you.